Induction motors hold significant importance in ships due to their reliable and efficient performance, making them a preferred choice for various on-board applications. Their robust design and ability to operate under varying load conditions are essential for maintaining the ship's operational capability. Additionally, induction motors require minimal maintenance, reducing downtime and operational costs, thereby contributing to the overall efficiency and sustainability of the vessel. The three-phase induction motor has two main parts. They are rotor and stator. The rotor is placed in the middle of the stator. Both stator and rotor are made up of cylindrical lamination core with parallel slots to reduce the hysteresis and eddy current losses. In three-phase induction motor, a three-phase supply connects to the three-phase winding of the stator. In the video, I have animated a 6-pole, three-phase induction motor. The power supply to this motor is provided in the star arrangement. Normally, the power for the induction motor is provided through various arrangements such as the star, delta, variable frequency drive, direct online, or soft starters. We will address each of these topics individually in future videos. The presence of a 120-degree phase difference between each phase of the three-phase supply, along with the specific arrangement of coils in the stator, leads to the generation of a rotating magnetic field. This field is always in clockwise direction. Because of this rotating magnetic field, the rotor will have an electromagnetic induction. Induction motors feature a rotor known as the squirrel cage rotor. This rotor is designed by arranging copper bars in parallel to each other but slightly skewed, ensuring optimal performance. The skewed arrangement enhances the motor's starting torque and reduces the chances of rotor lock during operation. The copper conductors of the rotor are formed in a closed circuit by being short-circuited at both ends using end rings. This arrangement allows the induced voltage to drive a current through the rotor conductors, following Faraday's first law. Then, according to Fleming's left-hand rule, a force is exerted on the rotor. The force developed on the rotor operates tangentially as the rotor is divided into slots by the copper bars placed around its circumference. So, a torque generates, and it turns the rotor to clockwise direction. When the rotor starts rotating, it tries to achieve the speed of the rotating magnetic field. When the rotor achieves the speed of the rotating magnetic field, the relative motion of the rotor and stator becomes zero. This phenomenon causes the stopping of the current induction of the rotor as the non-availability of the rate of change of flux on the rotor. When the current induction stops, the rotor loses the torque upon it. This slightly reduces its rotating speed and again starts to experience a relative motion with respect to the rotating magnetic field. So, all the time, the rotor rotates slightly slower than the rotating magnetic field. In other words, the rotating speed of the rotor does not synchronize with the speed of the stator's rotating magnetic field. Because of that, we call the three-phase induction motor an asynchronous motor, and they are self-starting motors. This speed difference between the rotor and stator is called a slip. Usually, a three-phase induction motor experiences a slip value from 2% to 6%. The rotating speed of the motor can change easily by changing the frequency of the supplied power to the stator using a variable frequency drive.
Thank you for joining us on this journey to unravel the mysteries of shipboard technology and machinery. If you found this video informative and engaging, don't forget to like, share, and subscribe to our channel. By doing so, you'll stay updated on all our latest content, and together, we'll continue to explore the fascinating world of maritime technology. Your support means the world to us.